The namespace resolution cache maintains an in-memory mapping of symbolic identifiers to their corresponding internal references. This cache operates as a transparent intermediary between the resolution layer and the backing store. Lookups against the cache are performed using consistent hashing to distribute entries across a fixed number of buckets. Cache misses trigger a synchronous store query with automatic result population. The cache does not differentiate between successful and failed resolution attempts. Both outcomes are stored with identical TTL constraints. Title-if parameters govern cache entry retention. The default TTL is 3,600 seconds. TTL begins upon initial insertion and proceeds monotonically forward without reset on subsequent hits. Entries reaching their TTL expiration are marked for eviction, but remain queryable until the next background sweep cycle. The sweep cycle executes asynchronously at intervals configurable via the cache.sweepInterval parameter with a default of 300 seconds. Expired entries may persist in the cache for up to 300 seconds beyond their nominal expiration time. Invalidation may be triggered through three mechanisms. Explicit invalidation occurs when client code invokes the invalidate method with a namespace identifier. Batch invalidation removes all entries matching a prefix pattern through prefix invalidate. Cascade invalidation propagates from dependent namespace entries when a parent identifier is invalidated. Cascade relationships are stored in a separate directed graph structure updated during cache population. Cascade invalidation does not recursively propagate beyond immediate dependence. The backing store interface defines a getNamespace method accepting a namespace key and returning either a resolved reference or a null sentinel value. This method is synchronous and blocking. The backing store is consulted only on cache misses and upon explicit refresh operations. No assumptions are made regarding backing store response time. Read timeouts are configurable via store.readTimeout.ms with a default of 5,000 milliseconds. Timeout violations result in a cache miss exception propagated to the caller. Memory constraints are managed through a bounded cache size and eviction policy. The cache maintains a maximum capacity of 100,000 entries by default, configurable via cache.maxEntries. When insertion would exceed this capacity, the eviction policy selects a victim entry for removal. The default eviction policy is least recently used, tracking access time for all cached items. LRU tracking incurs overhead proportional to the number of entries. Access times are updated in bounded constant time using a clock-based approximation algorithm. Alternative eviction policies are available through the cache.eviction policy parameter. The random policy selects eviction victims uniformly at random. The FIFO policy evicts oldest inserted entries first. The TTL-based policy prioritizes eviction of entries nearest their expiration time. Custom eviction policies may be implemented through the eviction policy interface, providing a select victim method. Policy selection occurs once at cache initialization and cannot be changed at runtime without full cache reset. Concurrency control ensures consistency across simultaneous access patterns. All cache operations are protected by reader-writer locks at the bucket level. Multiple concurrent readers are permitted for the same bucket. A writer acquires exclusive locks on the affected bucket. Lock acquisition uses non-blocking trilock semantics with configurable timeout via cache.lockTimeout.ms. Contention metrics are exposed through the locks held and locks weighted counters updated for observability purposes. The refresh operation retrieves the current state of a cached entry from the backing store regardless of cache validity. Refresh is invoked through the getFresh method with a namespace identifier. The refresh operation bypasses the local cache read path and directly queries the backing store. Upon successful retrieval, the entry is updated in the cache with a new timestamp. Failed refresh operations leave the cache entry unchanged and return an error sentinel to the caller. Cache statistics are continuously collected at the cache level. Hit and miss counts are maintained as monotonically increasing counters. Hit ratio is computed as hits divided by total lookups. Miss ratio equals 1 minus hit ratio. Eviction count tracks the cumulative number of entries removed due to capacity constraints. The statistics are exposed through the getStats method returning a frozen snapshot. Statistics are never reset during normal operation. Reset requires an explicit administrative call. Distributed cache scenarios introduce replication and coordination concerns. When multiple cache instances exist, invalidation operations must propagate across all instances. A distributed invalidation mechanism uses a publish-subscribe pattern over a shared event channel. Cache instances subscribe to invalidation topics corresponding to their managed namespaces. Subscription occurs at initialization and persists for the cache lifetime. Event ordering is not guaranteed across multiple instances. Eventual consistency is achieved within the cache TTL period. Serialization of cache entries is necessary for persistence and interprocess communication. Each cached entry is serialized to a byte sequence containing the namespace identifier, resolved reference, insertion timestamp, and TTL value. Serialization uses a binary format with fixed width fields, where possible to minimize overhead. Deserialization reconstructs the entry structure with full type fidelity. Serialization is transparent to cache clients. It occurs only during explicit snapshot operations initiated through the dump entries method. Error handling distinguishes between transient and permanent failures. Transient errors such as backing store timeouts are retried up to a configurable limit before reporting failure. Permanent errors such as malformed namespace identifiers are immediately reported without retry. The cache.max retries parameter controls retry attempts, defaulting to 3. Retry backoff uses exponential jitter with initial delay of 10 milliseconds. Error states do not affect cache validity for subsequently accessed entries. Configuration parameters are loaded at initialization time from a configuration file or environment. The configuration object is immutable after initialization. Parameters not specified explicitly receive default values as documented. Invalid parameter values raise an initialization exception preventing cache startup. The active configuration is accessible through the getConfig method for diagnostic purposes. Configuration changes require cache shutdown and restart. No hot reload capability is provided. Diagnostic tools are available for troubleshooting cache behavior. The cache dump command exports all current entries in human-readable format. The trace lookups method enables logging of all cache operations for a specified time window. Trace output records the operation type, key, result, and timing information. Tracing incurs measurable performance overhead and should be disabled in production after investigation. Diagnostic output is written to the configured logging sink without filtering. Cache lifecycle management includes initialization, operation, and shutdown phases. Initialization allocates memory structures and establishes connections to the backing store. The initialize method is idempotent. Calling it repeatedly on an initialized cache has no effect. The shutdown method gracefully terminates background operations and releases allocated resources. Shutdown allows an optional timeout parameter specifying maximum shutdown duration. Shutdown is synchronous and blocks until complete or timeout is exceeded. Performance characteristics of cache operations are documented for capacity planning. Lookup operations execute in expected constant time with respect to entry count. Insertion time is similarly bounded constant. Eviction selection time is proportional to the eviction policy complexity, with LRU requiring logarithmic time. Invalidation operations are linear in the number of affected entries. Cache overhead is approximately 200 bytes per entry for metadata structures. Actual memory usage depends on the size of namespace identifiers and resolved references.